common takeoff rating, maybe takeoff rating can be 101, 102%, something like this. But this is a choice, let's say, of the designer, of the manufacturer, to call this 100% rotational speed this or this rotational speed. It's not the maximum. It's a kind of maximum allowed by the way this engine is used. It's not a maximum compared to an explosion of the disc or explosion of the blades or something like this. It's more a nominal value that he's taking as this is my wish for 100%. And then he can go to 105, and very often working lower than 100%. So this 100% is not very clearly defined in general. Of course, it's clearly defined for each, let's say, engine type that you are considering. And so what I would like to understand, this is what is surge, what is the surge line, and what is rotating stall. You will see also that I will introduce a third phenomenon that is called the stagnation stall. A stagnation stall, which is, let's say, something else, another phenomenon than rotating stall and surge. So what are these phenomena? What are these phenomena? I will just remind you a very little bit what is the problem related to rotating stall and related to surge. So we take a compressor grid. So what is a compressor grid? This is this. This is this. So I take at a certain position, it can be the tip, it can be here in the middle, it can be at the foot, it can be there, I don't know, I cut the system, and my compressor is, oriented like this. My compressor is rotating, let's say, this direction. I could have taken a compressor rotating in the other direction, so it doesn't matter. So I take a certain compressor and I'm looking at the compressor from the top. And the compressor, the shaft of the compressor is there, and the compressor is rotating like this, or it can rotate in the other direction as well. And so I take a compressor, so the reference is what I call a chord, and then I put a certain shape on this chord, for example, something like that. The chord can be not equivalent with the the pressure side of the compressor, it doesn't matter. And here the compressor is rotating in this direction. We are, in fact, at a certain distance from the shaft. We are at a certain distance from the shaft, let's say with the disc here. And I am at this distance r, so in fact here it's not n, it's more u, which is equal to 2pn divided by 60 multiplied by r, multiplied by this distance. And I have, I don't know how many blades, of course. I'm trying to represent that a few times the same blade, with this, of course, the same distance between each blade. So this distance, this is the spacing between the different blades. So this is the pitch. And I represent here 4 blades, 4 times the same, blade 0, 1, 2, and 3, let's say. So this is a rotating blade. I could do the same also for non-rotating one. The fact that it's rotating or non-rotating, it doesn't matter. And my reference direction, this is the direction of the chord. And the reference direction is, let's say, for example, with this velocity triangle, where I have u here, I have the absolute speed always with a vector, but I'm forgetting that because I will have already a quite complicated drawing, and here the relative speed. Absolute velocity, tangential velocity, and the relative velocity. And of course it's rotating, I take a rotor, it's a rotor here. So the reference speed, this is the relative velocity, and so this is the important angle, this is the angle of attack of the relative velocity compared to the chord of the blade, okay? And you know that I'm always going to work, so these are non-symmetric blades, so such a non-symmetric blade, it has a CL in function of alpha, and the angle of attack which is like this, with here the alpha max, where I'm starting to have the boundary layer separation, and you know that I'm going to work in this region because I need to have a high pressure ratio, and the high pressure ratio is related with a high value of CL. So I'm going to work, let's say here. This is the position, this is the alpha working point that I have. And my fan is working, fantastic, extraordinary, I'm happy, I'm working like that during 2 years, 3 years, 4 years, no problem. And of course I'm not too far from alpha max, but it's not a problem. And that at a sudden, what's happening? I have at one place, it's not the case here, but I could show you blades where it's like this. A stone is coming, just one stone, very small one. One stone is coming and impacting just there, just here. So here I have the leading edge that is changed. You change the direction of the leading edge. The leading edge is normally like this, and the leading edge is becoming at one place something like this. So here, nothing wrong, here nothing wrong, just one place where you have this. And the second blade there, nothing. Third blade, nothing. Fourth blade, nothing. The blade before, nothing, nothing. Only one stone. So the stone is impacting this one and then leaving the engine. What's happening? This is, let's say, blade 1. If you are there, let's say you change the position of the cord and the stone is coming and the cord is at this position, let's say change in this direction. So referring to my drawing, it would be more something like this. Referring to the drawing. If I look it from the front, so it's up tilted like this. So you see the direction that is now my reference, this is this one. And the angle of attack here is becoming this angle of attack. So I was there, I'm now here. And so what's happening? On this blade, I'm having a boundary layer separation. Let's consider that I have the boundary layer separation at the back of the blade. So this is what is called a trailing edge separation. What's happening? I was sending, following this direction everywhere, following this direction everywhere, also in this one. I was sending, let's say I have, I don't know, 30 blades. I was sending m dot divided by 30 in each of these blades. What's happening here? You see, normally in a compressor you have somewhere here a throat. This is the throat area of this compressor. What have you done? By the boundary layer separation, you have changed the throat. The throat is not anymore the same. The throat is decreased. I will increase my boundary layer separation so that my drawing is very clear. So I have increased my boundary layer separation, and I have now this throat that is the new throat that is smaller than the old throat. So if I have a smaller throat, here I was sending m I was sending m dot divided by 30. I am now sending less. M dot divided by 30, this is, let's say, 3%. I am now sending, let's say, I say something easy, 1%, or 2% maybe, or 2.8%, I don't know. And if I was sending 2.8 instead of 3 before, that means that I try to send 0.1% here, and I try to send 0.1% here. Okay? These 0.1% are doing what? These 0.1% are doing what? Not so much influencing the mass flow rate. Here I had 3%, Now I have 3.1%. It's not so much of a problem. But mainly, it's not oriented anymore towards this direction. You see flow is coming from downward here. So I'm changing the direction of W on the blade number 2. What's happening on the blade number 0? I'm changing the direction in the good direction. So here on blade 2, I'm increasing the angle of attack. Here on blade 0, I'm decreasing the angle of attack. And so my stone has impacted only one blade. My stone has impacted one blade, but on the second blade that has not been impacted by the stone, you see that the flow is changing the direction due to the flow coming from in between 2 and 1. And so the angle of attack is increasing, and there also you will have boundary layer separation, even if the blade is fully correct. And so what will happen, again here, you will have, let's say, 2.8% instead of 3. So what will you have? 0.1% is going here, 0.1% is going there. It's not a problem of mass flow rate, it's a problem of direction. Here, angle of attack will increase, so you will also separate, and this is the important point, the 0.1% coming from there will re-establish the direction of the W velocity vector here, and you will again come back to the normal value of the angle of attack, and the boundary layer separation will disappear. And so you see what's happening. For one reason, I have taken here a stone. It can be icing. It can be also the blade that, I know it's not a compressor, but if a blade is starting having, let's say, tolerance in the movement here, one blade is changing its position, and if the blade is changing its position in this direction, only one of the 30 blades, I have also a problem there. There can be a lot of different reasons related to the blade or related to something happening before, like ice formation or things like that, or an obstacle or a side wind. I don't know, you can have a lot of different reasons. Distortion in the intake, there are a lot of different reasons. And you see that the blade that created the problem, is influencing a first one, maybe a second one, maybe a third one, and so they are starting all of them separating. It depends, you can have 2, 3 blades separating at the same moment, but in the opposite direction compared to the movement, in the direction of the rotation, you are re-establishing the flow. And so you see that you have a stall. This is the generic name that we give to a boundary layer separation. We have a stall, but this stall is rotating. That means it's increasing in this direction and is disappearing in the other direction. And so if you see the problem from the front, you create it here, and it's moving into the